Good evening, everyone. I'm Professor Andrei Zvelindovsky. I'm head of School of Mathematics and Physics in University of Lincoln, and I extend a very warm welcome to everyone who came to this live talk, live chat, Astro-Chat, which we organize in University of Lincoln. I see there are more and more people join, and welcome everyone. As usual, in this type of talks, you will have presentation, and then you will have time for questions. And those questions you can put below in a live chat on this YouTube video. Then I will read them to our distinguished guest. And you also can leave your comments after the talk and watch this live chat later. At any time, it will be kept here on YouTube. And I'm extremely pleased to have our already traditional speaker, Professor Don Kurtz. Hello, Don.
Hello, Andrei.
Don joined us via this video link from South Africa, where he is. So even we separated in space, we can meet and chat about interesting topic of astrophysics and astroworld. Some of our visitors are regular already, so you know Don very well, but each time some new comes, so I'll say just a few words about Don to introduce him to our audience. Professor Don Kurtz, originally from United States, in particular California, San Diego, where he received his education in astrophysics. Don has a long and distinguished career in the world in this field. He spent about quarter of a century in South Africa, and then almost another quarter of a century here in the United Kingdom, working in University of Central Lancashire. During this long and distinguished career, he published over 500 of scientific articles, publications, and he authored now classical, basically, a textbook on astroseismology, and very especially Don gives lectures all over the world, and I think the only continent where you did not give lecture is Antarctica. Is it right?
So far, that's true.
So, and just in the last 10 years, Don gave over 300 public lectures all over the place. In his career, he served also as a vice president of Royal Astronomical Society, and for his services to astronomy, in particular with his extremely prolific outreach and promoting astronomy, both with public but also with research, he was awarded Royal Astronomical Society 2022 Service Award for Astronomy. Congratulations, Don, with this very distinguished award, which was just awarded, I understood, last week or something, right? Is it correct?
That's correct. Thank you, Andrei.
And right now, Don, as I mentioned, physically located in South Africa, where he was appointed extraordinary professor in Northwest University. But also, we're very pleased that Don is a visiting professor of astrophysics here, University of Lincoln. And I myself, as everyone who came, I'm sure, really waiting for Don to tell us more about very exciting topics he finds for our monthly Astro Chats. Floor to you, Don.
Thank you, Andrei, and good evening, everyone. Just to put you in perspective, what life is like for me here in South Africa. The last couple of days, it's been 30 degrees, the sun's shining, the sky's blue. The surf is about 3 meters crashing into the Shorelines here of the most beautiful beaches in the world, and they're just empty of people. It's absolutely fantastic. So I'm sorry to be missing your winter, those of you who are near Lincoln. But then I guess I'm not really sorry. I'm enjoying the summer here. Tonight I want to tell you about neutron stars and pulsars. These are some of the most amazing or most exotic stars in the entire sky. And so just bear with me now while I start up my presentation. So we've got some slides to look at here. And if Andrei will confirm, we are now looking at my slides, Andrei?
Yes, they perfectly visible.
Right, and I just need to turn on my laser pointer. There we go. Oh, let's see, red should be okay. Neutron stars were predicted back in the 1930s, almost immediately after the subatomic particle, the neutron, was discovered. But it was another 30 years after the prediction before they were finally discovered. They remained purely theoretical through the 1930s, 1940s, 1950s, and well into the 1960s. I want to take you back to a slide I showed you in December when we talked about white dwarfs and remind you of the life cycles of stars. In our Milky Way, we have got on the order of 400 billion stars, but there's still plenty of gas, a little bit of dust left over, so new stars are still forming in the galaxy. They form out of gas clouds between the stars that occasionally get dense enough that gravity takes over and makes them start to collapse. Now, gravity is everywhere, and there's no escaping gravity. It's always there, it's always waiting. And so as the gas clouds collapse to become a star, the thing that stops their collapse is that the inside of the star heats until the gas pressure pushes out to balance the gravity pulling in. We call that in astronomy hydrostatic equilibrium. The sun is in that state now, and it produces the heat to generate the pressure to balance gravity by fusing the lightest element, hydrogen, to helium. And the sun will do that for about 10 billion years. It's currently halfway through that cycle. But as it creates the second heaviest element, helium, in its core, the core shrinks a little bit, it heats up, and the generation rate for the nuclear reactions is incredibly sensitive to temperature. And so with time, the sun is getting brighter and brighter and brighter. Some of the energy it's generating is also making it bigger and bigger, and so it's swelling to be a bright red giant star, which is what it will be in its old age. Now, if you've just had the thought, maybe this is the reason that we have climate change and global warming, the answer to that is no. We've looked at that question seriously, and it's not a change in the sun that's causing the current change in our climate. That's us pumping carbon dioxide into the atmosphere. But ultimately, the sun will swell to be a red giant. It will evaporate and swallow Mercury and Venus. It will cause the heat death of the Earth, blowing away our atmosphere and our oceans, melting the continents. And then at the end of its life, when the sun has converted hydrogen to helium and then helium to carbon in its core, it will collapse to be what's called a white dwarf. And that's what we talked about in December. In the white dwarf, the gas is in what we call a degenerate state, and it's no longer gas pressure that balances the gravity. The gravity has become incredibly strong in the white dwarf. Even though it has 6/10 the mass of the sun, it's only the size of the Earth. And the pressure that balances the gravity is called electron degeneracy pressure. It comes from something called the Pauli exclusion principle. We'll come back to that. The point now is 97% of all stars die as white dwarfs. Back in the 1930s, 1940s, 1950s, astronomers thought all stars, when they died, became white dwarfs. But with the discovery of neutron stars in the 1960s, we realized that's not the case. About 3% of stars that are very massive, 10 times the mass of the sun and above, as they live their lives, they fuse hydrogen to helium, helium to carbon, carbon and helium to oxygen, and they build up heavier elements till when they become red supergiants, in their cores are made of almost pure iron. Iron is the most densely packed nucleus. The stars can make energy by fusing lighter elements to heavier elements until they make iron. And then if you want to make elements heavier than iron, you have to put energy in. A star can't shine by doing that. And so as the core of the red supergiant squeezes, It heats and it heats and it heats until it reaches a temperature of a couple trillion degrees. And finally, at that temperature, there's so much energy just in the light that the iron gets torn apart back into helium. And that soaks up all the energy. We call it the iron catastrophe. And in a matter of about a microsecond, the core of the star collapses. It collapses initially to the size of a white dwarf, but the gravity is so strong, even the electrons can't resist the gravity. But the law of the universe, the Pauli exclusion principle, says the electrons cannot be packed any more tightly. The gravity is so strong, the electrons can't resist. And the universe has a way out of that. The electrons and the protons can be merged to make neutrons. And then the star collapses until it's only the size of a small city, 20 kilometers in diameter, and becomes what we call a neutron star. And that's what I'm going to talk to you about tonight. There is another death state for stars, even rarer, where the core collapses past the neutron star stage and becomes a black hole. And I'll talk to you about that death state for stars and black holes next month in the next Astro-Chat. We need to do a little basic physics to understand how neutron stars come to be. The two main forces that you and I are most used to and that dominate our macroscopic world are the gravitational force, which holds everything together. It's always attractive, and it reaches out to infinity. And the electromagnetic force, the force between protons and electrons that hold them together in atoms. Forces between protons and protons are repulsive because they have the same charge. Between protons and electrons, which have opposite charge, they're attractive. But as these two forces reach out into space, they pass through larger and larger areas and they become diluted. We call this the inverse square law. What this little equation here means is that the farther away you go from the gravitational or electromagnetic source, the weaker the force becomes, and it gets weaker with the distance squared. I made a little graph for you to show you how that happens. Here's the strength of gravity or electromagnetism, and here's distance between two objects, two gravitational objects. And the closer they get, the stronger the force. The farther they get, the weaker the force, all the way out to infinity. Those are forces that we're used to. That's the kind of force we think of. Get closer to something, the force gets stronger. Get farther away, it gets weaker. But that's not what holds the nuclei of atoms together. And so that's not what makes the periodic table. Here's an example of a carbon atom, a schematic cartoon. And it's held together by something called the strong nuclear force down in the nucleus. And the strong nuclear force is nothing like gravity, and it's nothing like electromagnetism. In this cartoon, the core of a carbon atom is made up of 6 positively charged protons and 6 neutral neutrons. And the size of the nucleus is about 1 femtometer. What's a femtometer? Well, you have a feeling for a meter. 1,000th of a meter is a millimeter. 1,000,000th of a meter is a micrometer. 1,000,000,000th of a meter is a nanometer. 1,000,000,000,000th of a meter is a picometer. And 1,000 trillionth or a quadrillionth of a meter is a femtometer. This is a tiny distance. The nucleus is packed into a femtometer, 1,000 million millionth of a meter in size. Let's put that in perspective. A lot of you will be in Lincoln or near Lincoln, given that this talk is going out through the University of Lincoln. And so let me use you as an example. If your head was the size of this nucleus, 1 femtometer in size, then the distance out to the electrons, this diagram is not in scale whatsoever. The distance out to the electrons, they would be at the distance of Miami, Florida. The atom is almost all space. So the electrical charge from the proton holds the negatively charged electrons in a cloud around the nucleus. And it's the nucleus we want to talk about now. It's the strong nuclear force I want to make a little more sense of. So here's a diagram, a little like the one that I just showed you for the gravitational force. This diagram shows distance of 2 nuclear particles, 2 protons, a proton and a neutron. And if they're about a femtometer apart, then the nuclear force is strongly attractive, and that's written as negative here. You can see it's very attractive. But as soon as you go 2 or 3 femtometers away, no distance at all, the nuclear force drops off to almost nothing. It only operates on a very tiny scale. If you have some other force, like gravity, and we'll come back to that in a neutron star, that squeezes the neutrons until they're essentially touching, once they get to where they're touching, they don't like that at all. And the strong nuclear force becomes repulsive, and that keeps them from getting any closer. So this is very unlike gravity and electromagnetism, which is just stronger as you get closer and weaker as you get further. Nuclear force, very strong at a short distance, disappears at slightly further distance, but if you try to make the particles squeeze into each other, it becomes repulsive. And that's what holds nuclei together and keeps them from collapsing also, this close repulsion. So let's talk about those particles that make up atoms. Our fundamental particles, the proton with a positive charge. Now the proton itself is not actually completely fundamental. We know it has structure inside of it. It's made up of three smaller things called quarks. The neutron, which is slightly more massive than the proton, is also made up of three different quarks, but the neutron has no charge. The electron's a truly fundamental particle. It has no interior structure. It's not made up of anything smaller, but it's only about 1/2000th the mass of the proton, but it holds exactly the same charge, just of opposite sign. And then there's another little particle we won't talk about too much today, but it's important in the nuclear physics. It's called a neutrino, and in this case, this one's an antiparticle of a neutrino. Neutrinos have almost no mass. They have a mass that's on the order of a 500,000th the mass of the electron, and the electron's got a mass of 2,000th that of the proton. So these things are just almost massless, and they travel at nearly the speed of light, and they almost do not interact with matter. They're created in nuclear reactions in the sun. Right now, hydrogen fusion in the sun generates neutrinos in huge numbers, and the sun's transparent to them. The Earth is transparent to them. You are transparent to them. At the moment, you have on the order of 100 trillion neutrinos passing through your body every second that have come from nuclear reactions in the sun just 8 minutes ago and streamed out across the space between the sun and us to be passing through the Earth and passing through your body now. An important thing for us right now is that that neutron in a nucleus is stable, but when it's all by itself, it's not stable. If you put a neutron out in space all by itself, on average, within about 10.2 minutes, it will decay, and it splits into a proton and an electron and one of these antineutrinos. So the neutron's actually made up of these other particles. That is the escape clause that allows neutron stars to form, and I'll come back to that. I told you last month, for those of you who weren't here, you're hearing it now for the first time, but electrons obey something called the Pauli exclusion principle, named after Wolfgang Pauli. You see, he lived in the first part of the 20th century. And electrons cannot be packed past a maximum density. No two electrons can have the same quantum state. And so in a white dwarf, when the electrons are packed, they're packed to the maximum density that the universe allows. They cannot be packed any more tightly because of this rule. And that then causes the electrons to resist gravity, and that's what holds up a white dwarf. But in the iron catastrophe, when the core of a giant star collapses, the energy released blasts that star to bits as a supernova. It explodes, and for a matter of weeks, it's brighter than the other 400 billion stars in its galaxy from the tremendous energy released from the gravity. As the core collapses past this white dwarf stage, how do the electrons get out of this problem? They can't be packed any more tightly, but they can't resist this incredible gravity. And the answer is the electrons and the protons get pushed into each other. They're turned into neutrons. And then no electrons to resist the gravity until the neutrons are packed to where no two neutrons can have the same quantum state. And then the neutrons resist the gravity. Also, the strong nuclear force, which is very repulsive at close distances, also resists the gravity. And so the star stops collapsing when it's about 20 kilometers in diameter, incredibly dense. It's phenomenally different from anything else we know in terms of stars, and we get a neutron star. The maximum mass that a white dwarf can have was calculated by Subramanian Chandrasekhar. It's about 40% bigger than the mass of our sun. Neutron stars are more massive than white dwarfs. The calculation of the maximum limit for that is named after 3 famous physicists, and it's on the order of 2.2 to 3 times the mass of the sun. It cannot be so exactly calculated as the Chandrasekhar mass. Some of you might recognize this name, Oppenheimer. Robert Oppenheimer led the Manhattan Project and the invention of the atomic bomb back during World War II. So let's look at some of the amazing facts about neutron stars. Typically twice the mass of the sun, but the size of a small city, meaning their densities are on the order of 1 billion tons per cubic centimeter. How to put that in perspective? Well, I did the calculation earlier just as we were waiting for this talk to start. If we took all 8 billion people on planet Earth and squashed us down to neutron star density, we would occupy less than a cubic centimeter. We would fit inside a thimble. The neutron star is mostly a degenerate neutron gas, just neutrons flowing around in this incredibly dense state. It's like a giant atomic nucleus. But on the outer part of the star, where it's not quite in this degenerate state, it forms a solid crust. This star is not completely gaseous like the sun. It's got a crust on the surface. Now, the Earth has a crust too, that's rock. In the case of the outer shell of the neutron star, it's mostly iron. It's basically got a roughly 100-meter thick steel shell as its surface. With a tiny atmosphere outside that, it's only microns, millionths of a millimeter thick, made either of carbon or of iron, maybe a bit of hydrogen on top of that. But a millionth of a meter on a neutron star is a long way. The surface gravity is 270 billion times that of the Earth. And so if we wanted to compare, say, Mount Everest here on the Earth, 8.8 kilometers above sea level, how high would you have to climb on a white dwarf to have the equivalent energy output of climbing Mount Everest here on the Earth from sea level? And the answer is about 0.3 of a micron, much less than the thickness of this atmosphere. Neutron stars spin fast, really fast, typically times per second, but the fast of them over 700 times per second. And as they've collapsed, they've condensed the magnetic field of the star they started with until it's a quadrillion times stronger than here on the Earth. They're phenomenally magnetic. The gravity is so strong that to escape the surface, you need an escape velocity of about 40% the speed of light. These stars are truly amazing. Here's a cartoon description of what the inside might be like. There's this outer crust of steel and other atoms. Inside that, there's this soup of neutrons with some protons and electrons. Neutrons still decay, protons and electrons still get squashed back together in a super liquid, which is completely viscosity free, just like a supercooled helium. And then the very inner core, where the gravity has squashed it to densities beyond the atomic nucleus, we don't actually understand nuclear physics at those densities well enough to do anything except speculate what that core may be like. It may be some new physics. Hyperons are just special particles like protons and neutrons that have things called strange quarks in them. That's conjecture. And then a thin atmosphere. Now, this tells you there are beams coming out of those, and it's the beams we want to talk about now. In 1968, I was an undergraduate student studying astrophysics at San Diego State University. There's a picture of the old entrance of the university. And we astronomy students were so keen on our classes that we were never late. We showed up early, and we would sit and talk to each other about the latest discoveries while waiting for the professor to arrive. And one day in class, my stellar astrophysics class, 1968, we were waiting for the professor, John Schott, to arrive, when my fellow student, Dave, said, "Have you heard, did you hear, they've discovered a star that spins in 1.3 seconds. And the rest of us students laughed at him and said, "Dave, you're a nutcase. You know, the sun takes 26 days to spin. If it span in 1.3 seconds, the surface would be going faster than the speed of light. It would fly apart. No way." They said, "Yes, it's really been discovered." Prof. John Schott came in. We said, "What's this business? Is this possibly true?" And he said, "It's true. You need to read the papers. A star spinning in 1.3 seconds has been discovered." Absolutely amazing. The discovery was the year before. in 1967. It took till 1968 to publish it. And the discoverer was Jocelyn Bell. She had discovered pulsars. Picture on the left there is Jocelyn as a graduate student at Cambridge. She was working in the group of Professor Tony Hewish, who had built the Cambridge Radio Observatory. And they were studying scintillation. They were studying the way radio waves travel through the galaxy, flicker and scintillate, a bit like the way stars twinkle as starlight comes through the Earth's atmosphere. When Jocelyn, one night observing, discovered a signal in one of her objects she was looking at that was going blink, 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 every 1.33 ... out to 8 decimal places seconds, exactly repeating. She, her Professor Tony Hewish, the other people in the group tried to figure out what this thing could be, and the signal was so regular, their first thought was they had actually found evidence of LGM. What are LGM? Little green men. They thought they had found a signal from intelligent life somewhere else in the universe. That would have just been a phenomenal discovery. We're still hoping that's going to happen in some way or another, but it didn't turn out to be the case with the pulsars. Jocelyn's supervisor, Tony Hewish, published a main paper a year later on that, showing that the pulsars were best described as neutron stars, which had been discovered, or had been predicted back in the 1930s. And it was only 1974, only a few years later, that Tony Hewish was awarded the Nobel Prize for that discovery. There was controversy over that Jocelyn, being the one who was at the telescope and first saw these things, should have been included in the Nobel Prize. She herself said that she doesn't think so. She's had an illustrious career. She is professor at Oxford now. She's been president of the Royal Astronomical Society. She's a fellow of the Royal Society, had a very illustrious career. And very recently, Yuri Milner, who founded the Breakthrough Prizes, which he hopes and probably will become competitive with the Nobel Prizes, awarded Jocelyn a special Breakthrough Prize for the discovery of pulsars. That came in addition to the prize with $3 million. And what did Jocelyn do with her $3 million? She gave it to the Institute of Physics for bursaries for disadvantaged students, women in particular, but not only women, who are underrepresented in astronomy. She gave the money away. There's an artist's impression of what a pulsar looks like. It's a neutron star that's come from this incredible collapse. The magnetic field has been made quadrillion times stronger than the Earth's magnetic field, and there are beams shooting out of the two poles where the magnetic fields are, and the star's rotating. It's like a giant lighthouse in the sky, and each time the beam comes by, you see the star blink. This is the Crab Nebula in Taurus. This is what we see now. In 1054, the imperial astronomer in the Chinese court in China saw rise in the morning a star that he could see in the middle of the day. It was brighter than Venus, easily visible during the day for weeks, and at the position of what he called a guest star, also recorded in other cultures around the world. We now see this remnant. It was a supernova explosion, and it's incredibly bright. In the visible light, it's 10,000 times brighter than the sun, but there's no obvious energy source. In all wavelengths, X-rays, radio waves, visible light, it's 100,000 times brighter than the sun. Where does the energy come from? And the answer came when a pulsar was discovered at the heart of the Crab Nebula, spinning 30 times per second. Here's a combination of a Hubble Space Telescope picture plus a Compton X-ray satellite picture of the heart where the pulsar is, the disks spinning around in the middle of the nebula, the jets shooting out. And here's a nice little animation in visible light. This star blinks once in a 30th of a second. So here in the middle, there's a visible picture, which has now stroboscopically been presented to you. And you can see the star getting brighter and dimmer. As one beam comes by, you get a bright flash. That's when the beam points almost towards you, but because of the tip of the star, the other beam doesn't quite point towards us. And so that little flash is not as bright. And if you watch here, you'll see a bright flash and a dimmer one. It comes. Over here in this plot, it's just a two-dimensional plot of the picture, and you can see it come up bright and then there's the dimmer one. So that pulsar is spinning 30 times per second, but it's slowing down. As it spins electrons up to nearly the speed of light, throws them off the star. It's losing angular momentum, and it's throwing energy out into this nebula. And the rate at which it's slowing down actually generates enough energy to power this nebula at 100,000 times the brightness of the sun. Absolutely phenomenal. That pulsar is one giant flywheel. And as it slows down, it's the rotational energy that powers the supernova remnant. Pulsars slow down with time, but then they have what we call glitches. So here's a diagram for what's called the Vela Pulsar in the constellation Vela. Its period is a little less than 1/10 of a second, and this is how long the period is. And this is time over a couple of years when it was being observed with the radio telescope, and you can see the period's getting longer and longer and longer until all of a sudden there's just a glitch, and all of a sudden the period sped up. And then it went back to just getting slower, longer and longer and longer. First, guess what happened? With the incredible gravity and with a solid steel surface, as the neutron star slows down, it does have a slight bulge because of its spin. And as it slows down, it relaxes gravitationally and the surface cracks and you get something called a starquake. That was the first idea. That's not completely eliminated. More likely now it's thought that there are tornadoes inside the neutron star, vortices of superfluid neutrons that get attached to the outer shell, and as the star slows down, they can break free, and that causes the glitch. So neutron stars have glitches, things go on inside them, a big jump in the period, and then it continues slowing down with time. A physicist who decided he'd try his hand at writing some science fiction novels, Robert Forward, wrote 2 novels. First one called Dragon's Egg, about a neutron star that just happened to pass close to the solar system. And then he followed it up with a sequel called Starquake. And the idea came from a physicist named Tommy Gold, who speculated that the nuclei in the surface of a neutron star could have a chemistry that might allow biochemistry, life. Totally speculative, but enough for a science fiction novel. And both of these novels have got appendices with lots of descriptions of neutron stars. And so if you like science fiction, but you like hard science fiction where the neutron stars are in there, there's a couple of novels for you. I think they're still in print. And finally, neutron stars are not always by themselves. Sometimes 2 stars orbiting each other. It's common, most stars in the sky are double. Both explode as supernovae and produce neutron stars, and then the 2 neutron stars orbit about each other, and they are phenomenally good clocks. They are as good a clock as an atomic clock here on the Earth. And so, 2 astronomers, Joseph Taylor, the supervisor, Russell Hulse, his PhD student, discovered a binary pulsar with 2 pulsars orbiting each other. Russell Hulse was at the telescope, very much like Jocelyn was for the first pulsar. And so he discovered that the period of these pulsars was periodically getting faster and slower, shorter and longer as they orbited each other. And he realized that was just Doppler effect as they orbited. And the orbit was shrinking. And it was shrinking by exactly the amount predicted by Einstein's theory of general relativity. They had found proof of the existence of gravitational waves. That led to the Nobel Prize for the 2 of them, including the graduate student this time, Roger Hulse. Is that because the Nobel Prize Committee had learned its lesson over a few years since Jocelyn not being included? Or is it because Russell was male and Jocelyn was female? Nobody knows. I don't think it's very important to know that. But in this case, the graduate student, Russell, was included. That was the first proof that gravitational waves exist. Nowadays, gravitational waves are actually detected, and one of the major sources for them is shrinking orbits of binary neutron stars that then collide with each other and explode, producing a lot of the heavy elements in the universe at the time. Neutron stars and pulsars are absolutely fantastic, and it's time now, folks, for your questions. I'm sure that will have generated some. Thanks for your attention. Andrei, where are you? I need you back. And there, I should be back too now. Oh, I'm not hearing you, Andrei.
Oh, now you should hear me.
There we go. Thank you.
Right. Okay. Thank you very much, Don, for exciting talk as always. And we already have some questions arriving in the live chat. So I just again I invite everyone to type in your questions live chat, and now we have time to answer those. So there is a question from Maria Ekman, who is asking, is a nebula and magnetar star the same thing?
Sorry, ask me that question again, Andrei. Is a nebula and?
Magnetar star.
No, who's the person who asked, Andrei?
It's Maria Ekman.
Maria, no, it's not. The magnetic star, the magnetar, is the pulsar down at the center of the nebula. And so it's only 20 kilometers in diameter, spinning very fast. The nebula is absolutely gigantic. It's spread out into space over great distances. And that can be seen even through a small telescope with your eye. If you had a small amateur telescope and you look at the Crab Nebula, you can see the little fuzzy patch. There's no way you'd ever see the tiny little white dwarf, neutron star down in the middle. So the nebula is the remnant of the outer parts of the star that exploded. The neutron star down in the middle, the magnetar, is the remnant of the core, which collapsed to be a neutron star. They're two different things.
Thank you, Don. And then Maria, I have an extra question. How small small object like this could become a pulsar? What triggers that?
The trigger for the object to become so small, Maria, is the gravitational collapse, when the inside of the giant star heats to the point that the iron gets torn apart into helium. And that uses up so much energy that the core of the star cools catastrophically. And all of a sudden, there's no gas pressure. And gravity's sitting there waiting. Gravity's always there waiting. And as soon as the gas pressure gets turned off, the gravity causes the core to collapse. And the gravity is so strong, it squeezes all the protons and electrons together until they're neutrons and squashes the whole thing down to the size of a neutron star.
Thank you. And then there was a question from Tom G. Are all neutron stars also pulsars?
Thank you, Tom. The answer is no. When neutron stars first form in the collapse down in the core, they almost certainly at that point will be pulsars, and they typically will be spinning many times per second. But as time goes on and they slow down, they shed that rotational energy. Old pulsars will, old neutron stars will slow down until they're spinning with periods of 4 seconds, 10 seconds, and longer. And when they finally spin very slowly, the pulsing also turns off. And so the ancient neutron stars will not be pulsars, and probably the galaxy's full of those, and we just can't see them.
Thank you. Thank you, Don. There is a question from Fernando Schwindwein. How fast does the collapse occur?
Fernando, thank you. About 1 microsecond.
Pretty fast.
And interestingly, since you asked that, the gravitational energy released largely flows out. The energy comes out as neutrinos to start with. And the star is so dense, it's even opaque to those neutrinos, even though you and I aren't. In that 1/1,000,000th of a second during the collapse, the core of that star is at that moment producing more energy than the rest of the visible universe for that 1 microsecond.
Thank you. This question from Jack Herbert. Could a neutron star be the cause of the wow signal?
The wow signal. I'm sorry, is that Jack?
Jack, yes.
Yeah, there has recently been a new theory of the wow signal, and I can't remember at the moment what it is. Jack, hang on with me. Let's have a look for that, because I recently read about the wow signal again, and I've now forgotten and can't answer you immediately. So wow signal, strong narrow radio band signal, and what is the latest idea on it? Jack, I can't answer that one right off the top of my head. Maybe at another time in the future when I'm talking about something else and it's relevant, it'll come back up and I'll have looked it up for you. Sorry.
It's okay.
So the rest of you, the WOW signal was an amazing radio signal, and the person who saw this big spike in the incoming radio signal wrote "wow" on the paper chart where it was recorded. That's why it's called the WOW signal.
Thank you. Then there is a quite long question from public member AC. On Earth, magnetic field is likely caused by electrical conductive laws of magna. In neutron stars, if electrons are condensed into electrically neutral neutrons at no charge, what generates its field?
If this is AC, is this AC from San Diego? While you're looking for that, I will answer this. AC. The magnetic field in the neutron star originates with the star that collapses. Now, that didn't answer your question, because your question now is, where does the star get its magnetic field? And in the case of a star like the sun generates a magnetic field with a dynamo. So it's got flowing electrical particles, and we think the seat of that dynamo is beneath its outer convection zone, which is about 30% of the way down towards the core. So here on the Earth, the magnetic field is generated by currents flowing in conductors in the molten outer core of the Earth. In a typical star like the sun, the magnetic field of the sun, which is similar in strength to that of the Earth, is generated by a dynamo down inside the sun. For a massive star that becomes a neutron star, there's no outer convection zone. We don't think the magnetic fields are generated by a dynamo. We think the magnetic field is captured from primordial magnetic field in the interstellar medium. And so the magnetic field of that star is not so strong. But when you collapse that star from being 10 times the diameter of the sun to being 20 kilometers in diameter, the magnetic field gets crushed, and that squeezes it up to where it's got a magnetic field strength of a trillion or a quadrillion times the original magnetic field strength. And so it's a primordial magnetic field. It hasn't got a dynamo generating it, and it will decay with time. And that's another thing that turns the pulsars off with time, is the magnetic field will decay.
Thank you, Don. I actually squeezed a tiny question from myself. You mentioned like a fluid of neutrons in pulsar. You said that this is they're superfluidous.
Yeah.
How kind of basically, how do we know that? What came to this kind of suggestion that they're superfluidous, that they don't dissipate energy?
Okay, well, first of all, Andrei, at nuclear densities, they must be superfluid. I'll answer that in a moment. But just for everybody else who's listening, we can create superfluids here on the Earth. When helium is cooled down to a temperature of 1 or 2 degrees above absolute zero, minus 270, it becomes a superfluid. It has no viscosity whatsoever. And you can't keep it in the container it's in. It'll crawl right up over the edges in spite of gravity. And if you start it spinning, it will just keep spinning. There's no viscosity there. And so inside that neutron star, Andrei, if you've got degenerate neutrons, they cannot change momentum states. They can't change energy states. And viscosity comes from particles interacting and exchanging energy. And the only way 2 neutrons can exchange energy, if one becomes like the other and the other becomes like the first one, and they're identical, they're all neutrons. All neutrons look alike. They cannot change their energy state, and so they can't be viscous.
Thank you, Don. It's very, I think it's very kind of short but very nice explanation of superfluidity. So I hope our public also enjoyed that element. I see there is a question from, just a second, oh yes, from, by the way, AC indeed is from San Diego.
Okay. So AC will know that facade of San Diego State University. Just to a point, AC, In my second year, I used to sit out on that balcony up there in the break in my second year German class. That's quite familiar territory for me. Go ahead, Andrei.
A question now from Sean Childs. What happens then they die?
The neutron stars, when they die, Sean, all that happens is that they lose energy by slowing down. They're shedding energy, losing rotational energy. And there's a little bit of heat energy left in the atmosphere so that they can shine with some visible light. And they will just continue to cool and cool and cool and cool and get darker and darker and darker. If the proton, and hence the neutron, are stable particles, then that's it forever. If, on the other hand, the proton eventually decays, we already know it's got a lifetime longer than 10 to the 32 years, but if the proton eventually decays, then gazillions of years in the future, I mean, unimaginably far in the future, if the particles decay, they would decay ultimately into photons and neutrinos, and the stretching of the universe would stretch those to lower and lower and lower energy until they just fade away and they aren't anymore. And that's not a very satisfying answer. I'm sorry that it looks like that's the way the universe is.
Thank you. There's a connected question from Richard Brooks, who asked, what stops a neutron star collapsing into a black hole?
Thank you, Richard. The answer is that the neutron degeneracy pressure plus the strong nuclear force resist gravity. But you remember during the slides, I showed you that there's a limit to the maximum size a neutron star can have, somewhere around 2.2 times the mass of the sun, maybe as big as 3. If the collapse during the supernova explosion of the core of the star has more than that limit, more than the 2.2 or 3 solar masses, then the answer is nothing can stop the collapse from becoming a black hole, and it does become a black hole, and that is the topic of next month's Astro-Chat.
Thank you. Now there is a question from Stephen Chapman, who asks, hi Don, great to hear from you again. My son asks why the pulsars have the lights coming out of them.
Have the lights coming out of them? Oh, Stephen, is that your son's question or your question?
It's his son's question.
Okay, I thought so. Stephen, for the rest of you in the audience, Stephen has a PhD in solar physics from the University of Central Lancashire, and I think you overlapped with him also there, Andrei.
Yes, so, it's true.
Yeah. Okay, the answer to Steve, you didn't, what's Stephen's son's name? Type that in for me, Stephen. What's
Chapman.
your son's name? No, Chapman's Stephen's last name. That's not his son's first name.
Oh, let's see if Stephen will type it.
Okay, let me answer the question. Stephen's son, you can be for now, Stevenson. The electrons in the atmosphere of the neutron star are trapped in the magnetic field. And as the neutron star spins at this incredible speed, the electrons are flung away from the star. They're flung out, but still trapped in the magnetic field until they sped up almost to the speed of light. And as they're accelerated at this incredibly high speed, accelerating electrons emit radio waves. It's called synchrotron radiation because back in the 1950s, we had particle accelerators called synchrotrons, and that's where we first observed it in the physics lab. And so the beams coming out from the neutron stars, from the pulsars, are primarily radio waves. And the radio waves are synchrotron radiation, radio waves generated by the acceleration of these electrons spinning trapped in those strong magnetic fields around the neutron star. Now, let me just continue with that. The magnetic fields reach straight up off the surface near the poles. And so the electrons can move along the magnetic field lines better than across them. And they move out along the poles, and that's why you get the main beams along the poles. That's why you get the 2 searchlights.
Thank you. Thank you, Don. This question I see from Team Play, who asks, is it possible to see neutron star from the Earth?
Invisible light, is that the question, Tim?
It's just put extra information without special stuff.
Oh, okay. No, the neutron stars are primarily seen, and I mean see in exactly the way you use it too, but in radio waves. Now, you cannot see radio waves with your eyes, but they're electromagnetic radiation. They're just like light, just longer wavelength. And our radio telescopes see the neutron stars just fine. Could you go to the telescope and look through the telescope with your eye and see a neutron star? And at the moment, I would say they're pretty much too faint. The Crab Pulsar is visible in visible light, and I showed you a little movie of it blinking in visible light, but that's seen with a very, very big telescope and with a very sensitive detector. I suspect, I'm guessing at this now, I suspect that your eye is not a sensitive enough detector to actually see the little spot of the neutron star with your eye, even through the biggest telescope. When telescopes get bigger, someday, can somebody look with their eye through a big telescope and see a neutron star? And the answer is no. The biggest telescope being built on Earth now is the European Extremely Large Telescope. It'll be 39 meters in diameter. But just like the big 10-meter telescopes we've already got, there is no eyepiece. No human has ever looked through one of those telescopes. When we operate the 10-meter telescopes, I go to Chile to use 8-meter Very Large Telescope. I go to Hawaii to use the 8-meter Japanese Subaru telescope. Those things cost 50,000 pounds a night to run them. And if it had an eyepiece and I had my eye at the eyepiece and the light's going into my eye, I'm wasting your tax money paying for running this thing because I'm not getting science out of that. And so we don't even build eyepieces on the giant telescopes. All of the light goes to the instruments, so we maximize the science. They're too expensive to let people just go look through them, unless you've got a billionaire friend who might like to build such a thing and put an eyepiece on it for private use. I mean, they're building rocket ships to take themselves into space. They could do that.
Thank you, Don. And it's the right answer from Stephen Chapman, who says, my son's name is Isaac.
Well, good evening, Isaac Chapman. Nice to meet you. I hope to see you in person one day, along with you, Stephen.
Thank you, Don. I just kind of wanted to add a bit of comment. It's, of course, very fascinating discovery made by Jocelyn Bell, and also the story of Nobel Prize, and this more recent prize when she finally received from another rich person foundation. And the story I want to mention, then I was an undergraduate student, we've been told that was an interesting event once on one of international astrophysics meeting between Joseph Shklovsky, quite famous Soviet astrophysicist who also co-authored once the revised book with Carl Sagan, when Jocelyn Bell and her supervisor happened to be in that meeting, and Shklovsky was there as well. And being quite kind of strict Soviet astrophysicist, he straight went towards Jocelyn, passing by without saying anything to her supervisor, and start talking to Jocelyn about her work. Some of us kind of in Soviet Union thought in this way he tried to give her in a way sign of appreciation of that discovery which she made.
Andrei, but you should not. Tony Hughes should not be slighted. He developed the telescope. He started the project. He understood the physics. I mean, he deserved that prize. The question is only, should Jocelyn have been included for the discovery? But there's absolutely no doubt he was the worthy recipient of that prize. Just as an aside, I was sitting next to him at dinner just a couple of years ago in London. And during dinner, did we talk about pulsars? And the answer is no, we talked about sailing.
Right.
We physicists don't always talk shop when we're dining together. And oh, by the way, too, Tony died last year. He was 93, and he died last September.
Right. There is a question from Philriggs. How many pulsars do we detect in our Milky Way, and what effect are there if normal sound comes close to a neutron star?
Okay, the first answer, Phil, is that we certainly, I don't know what the modern number is, but it's certainly more than 1,000. And it's probably in thousands. And if a neutron star should come close to the sun, well, first let's get in perspective how far stars are apart. The nearest star to the sun right now that we know of, if there was a dark neutron star or black hole, it could be lurking. But just the general density of stars out here where we are, the nearest star at 4.3 light years, let's put it in perspective. If I shrink your head, the sun down to the size of your head, and Alpha Centauri down to the size of my head, then to scale, your head is, let's say you're in Lincoln, if you are. My head wouldn't be as far away as South Africa here, but it'd be somewhere around Cairo. The stars are a long, long way apart. And so collisions between stars out in our part of the galaxy basically don't happen. Down in the center of the galaxy, yes. And so let's talk about the center of the galaxy. What would happen in the incredible density of stars down the center of the galaxy if a neutron star got close to another star? And incredible tides would be raised. And the more interesting extension of this question is what happens when a black hole down in the center of the galaxy gets close to another star. Then the tides can tear that star apart and the black hole can eat it and can grow. And again, that's the topic next month. We're going to come back to that.
Thank you, Don. We still have time for questions. There is a question from John Levenhall. Don, you answered AC's question, but what holds the magnetic field of a neutron star? If there some part of the structure that remains magnetic?
The star as a whole remains magnetic, but now you're asking me a hard question. You're asking me, for example, it's a basically dipolar field. Does that dipole pass right through the center of the star and through the superfluid, or is it in some way confined to the outer part where there are electrically charged particles? And I have to admit, I don't know the answer to that now that you've asked me that. It's certainly dipolar on the outside, but whether that dipole field is confined to the protons and electrons in the outer part of the star in some way, or whether it penetrates right through the superfluid is not a question I know the answer to, but other people do. So I'm just telling you I'm ignorant of the answer.
Thank you. So there is a question again from AC who says, could that micron carbon atmosphere be a diamond atmosphere?
Oh, I don't think so, AC, in this case. The diamond atmosphere that we talked about last month in December in the white dwarfs is because the nuclei inside the white dwarf are not degenerate. They're actually still freely moving. It's only the electrons that are in their final degenerate Pauli exclusion principle state. And the nuclei in the white dwarf, which are mostly carbon, finally settle into a lattice, which is like giant diamond. In the outer part of the neutron star, could we have a degenerate non-nuclear gas? I don't think so. If you could, I think that the layer would be almost infinitesimally thin, because the outer shell, which is not non-degenerate, that forms that outer steel nuclei shell, is still hundreds of meters thick. And the region where it could just be in that state where it'd be going from degenerate to non-degenerate, I mean, we're talking about probably not even microns thick. AC, I'm guessing this. I mean, I'm now doing some hand waving, but I think not.
Thank you, Don. Just time is approaching the end. I have a small question myself. You mentioned the upper boundary of neutron star is not precisely determined. Where this kind of so for Chandrasekhar limit, you can have 1.4 quite sharp, but upper limit for neutron star is not so well defined.
You mean for the mass?
So
yeah.
Where this kind of so to say error bar comes from?
It's not an error bar, Andrei. It's simply that the physics is so difficult that it's not possible just to calculate the upper limit. The physics that Chandrasekhar first did for the degenerate electrons is actually relatively simple. We do that even in third-year undergraduate astrophysics and calculate the Chandrasekhar limit. If it weren't for the complications of the nuclear physics, then the Chandrasekhar limit extended to the neutron stars would suggest 4 times the Chandrasekhar limit. But other forces come into play, and if you want the answer to that, Andrei, it's tough. Go back to Tolman, Oppenheimer, and their papers from the 1930s, and those problems in nuclear physics are not fully solved, and that's why that upper limit's not absolute. But it's around 2.2, and currently it's set at that level because the most massive neutron star that mass has been measured for is 2.24 solar masses. If a 2.5 solar mass neutron star is found, then the physics can be fiddled with, and that will then be the new upper limit.
Thank you. Although we passed time, but there is a final question, maybe very short, from NCT. Do neutron stars have moons?
How about planets, moons? What would you call them? The answer is yes. The very first planets found orbiting another star were found orbiting a neutron star. And the reason that was possible is because the neutron star is such an incredibly fine clock that Andrew Lyons, who made that discovery, was able to see that this clock was being sped up and slowed down as it came towards us and moved away because it was orbiting something the size of a planet, and it could be precisely measured. So the first exoplanets were around a neutron star, yes. A moon, well, the moon would have to be around the planet because that's the way we define moons, and they're probably there.
Thank you, Don. As always, we enjoyed very nice chat with questions. We might not be able to answer all of those, but time is up, and you can still type your comments and even questions in a comments box below this video, and we will pass to Don. And I would like to thank Don again for his wonderful talk. I also pass comment from Minerva Bird, who say, thank you, Don, enjoying that ocean surf. And I do thank all of our audience who came today, and we hope to see you next month or in some other time in future for our future Astro-Chat with Professor Don Kurtz. Thank you, Don, and thank you, everyone.
Okay, thank you, everyone, for coming. Thank you, Andrei, for hosting it. Good night, everyone. Well, good night. Yes, it's night for me, too. Not for you, AC in California. Good day to you. Okay, bye now.
Bye.